peoples, ladies and gentlemen. Time has come for us to go ahead and get started today. So that's what I heard from a friend of mine, your professor.
He's besties with us.
Anyways, he said y'all started gases. So guess what we're gonna start today? Gases. No, but by the looks of it on this last exam, I think I need to do more balancing equation practice. Not you. I'm not looking at. I'm talking to you. Because when you talk to someone, you look at them. Anyways. All right. So I'm gonna let y'all work on 14A for about 2 minutes. It's really, really easy. You should be able to get this one in probably 2 minutes. So I'll give you all y'all's time to do your thing like 21. I want to work for finishing in 25 minutes. It was like 25 minutes.
No.
No, because it was like 6:30 right now. Yeah, 6:30. But I did start a little bit, so like 5 minutes. Yeah, you never experienced that last night.
No, that's why I'm like scared.
That's-
That's what I was saying. So like, does it get counted into like?
We're not trying to get demonetized.
You're telling me to say that we're down, no?
I wouldn't say it. Anyway. Well, I know you already said you would.
No, he said he would. I sent over.
He wrote got me so confused because I hear the right answers and then he said ever since I was right. That was wrong.
Sounds like him.
Oh, well.
Sounds like him.
No, but I was like, wait, because he said it couldn't happen. That's why I was like, oh god.
One minute. All right, so carbon tetrachloride, CCl4 can be synthesized according to the reaction represented above. A chemist runs the reaction at a constant temperature of 120 degrees Celsius in a rigid 25-liter container. That's a big container, by the way. I mean, think about that. Anyways. Chlorine gas is initially present in the container at a pressure of 0.4 atmospheres. How many moles of chlorine gas are in the container? So we got a couple variables that we got to work with. Let's highlight all of our important information. What variable is this? So T. What about this? Volume, yep, so V. And we're also given what? Pressure. All right. So it's asking, and what is it asking for? It's asking for moles of Cl2. And what variable do we assign moles? N. Perfect. So this is N. From memorizing all the gas equations, we would know that there's only one equation that encompasses all of these variables. Which equation is that? PV nRT or PV? PV equals nRT.
Yeah, that.
Or whatever you want to call it.
So pressure times volume is equal to the moles times RT. Okay. Anyways. We're looking for what variable? And that is what variable? Thank you. And so to do that, we have to algebraically solve for n, which I'm not going to do the work to solve for it because I believe that we should all know how to do that. If you want me to do the work, I'll go and show you. But once you algebraically solve for n, you should get this. At this point, it's just inputting everything into your equation. So our so this is equal to PV over RT, which is also the same as 0.40 ATM times the volume 25 liters divided by the temperature. What is the temperature? That is true. And we have to convert to Kelvin, right? So what's our conversion from Celsius to Kelvin? So 120 plus 273. Did you say you don't know something?
I don't know what you.
Oh, yeah, so when you do
Or you have a calculator, you can solve it.
Yeah.
oh wait,
Oh.
anyways, you should get 393.15 Kelvin. All right, let's plug that into here.
Why do we have to convert to Kelvin? Why can't we just leave it in Celsius? Why?
Why?
Well, what's the units of R? Why does it want Kelvin? That's the question. I mean, just because you like something doesn't mean like you won't roll the other way. You know what I'm saying?
You don't know how to eat it. So it's the same way. If I like.
I mean-
food, I'm only gonna stuff.
I mean, it's an acquired taste though. Like once you get it more and more.
Anyway, let's stay on topic. Why is it in Kelvin range?
Well, there's a little constant known as R, and the units of your R, or the magnitude of it is 0.0821, but the units are atmospheres times liters over moles times Kelvin. So the reason you want it in Kelvin is because the two temperatures cancel out, the Kelvin on the top and the Kelvin on the bottom.
Exactly. Therefore, that's why it should be in Kelvin. Not because it's the preferred units. It's because it's the only unit that works with this problem, because the constant R is derived when using temperature in Kelvin. I'm sure there's another R constant that can be used in Celsius, but the one we're using for our class is going to be in Kelvin. So you need to convert to Kelvin.
There's like a million R's, by the way. So like this one's what the one you're gonna use for this class. When you take Gen Chem 2, you'll learn about another R that you can use. And yeah, there's only two of them.
All right, so when you put this into a calculator, you should get about 0.31 moles of Cl2. Boom, got it. All right, if there's no questions, go ahead and we'll go move on to the next one. Good. Okay. How would you do B? Moles to grams. So moles of CO2 to grams of CO2. Okay. All right, so you're on the right track, except we're trying to convert to grams of carbon. Exactly. So let's start with what we're given. So 0.31 moles. Well, this is not what we're given, this is what we found, right? So 3 moles or 0.31 moles of CO2. And to convert from moles of CO2 to moles of sulfur carbon disulfide, we need to use the ratio mole ratio in the balanced chemical equation. So that's we already gave it to you. It's a 3-to-1 ratio, or 1:3. So 1 mole of CS2 is going to require or react with 3 moles of Cl2. And the molar mass, or 1 mole of CS2, And the molar mass of CS2 is 76.131 grams, which is going to give you an answer of about 7.8 or 7.9 after rounding. So 7.9 joules. All right. If there is no questions. You know why we did that? Okay, cool.
Why didn't we do that?
1 gram. You don't want to reach it. I was on this a little second.
Interesting. Okay. All
I
right.
mean, it's so nice, you gotta say it twice.
Okay. So I'll give y'all number 15. Or let y'all do number 15. I'll give y'all, let's do 3 minutes. Please try it like your best of, to the best of your ability. Are you sure? Okay.
All right, let's do this. If 38.5 milliliters of lead-2 nitrate solution reacts completely with excess sodium iodide solution to yield this much precipitate, what is the molarity of lead-2 ion in the original solution? All right, so what was the first step in doing this? Let me do the game plan here. Step one. What was step one? There's something you could do before that.
There we go.
Write a balanced chemical equation. So in this case, we're going to do PbNO3 2 plus sodium iodide makes PbI2 plus NaNO3. Is this equation balanced? How would you balance it? Or what coefficient would you use? Exactly. So 2 right here. Then let's fill out our physical states. Aqueous. Is this soluble or insoluble? Sodium nitrate. It is. Why?
Nitrate.
Yep. And then what about our lead-2 iodide? Soluble or insoluble? Why?
Because of like, the lead is different from iron.
Yeah, so it's lead 2 plus, normally soluble, silver plus, mercury, something like that, and then copper plus. All right. So step one, balanced chemical equation. That's out of the way.
Is it balanced? You
No. No.
gotta speak up.
What you was talking?
Don't interrupt us.
Exactly.
It's not relevant.
Well, what else do you have to do?
Yeah.
Oh, you gotta flip it.
Sodium on Tuesday. So what will you do to balance?
And put a 2 right there. Now is this equation balanced? All right. Step 2. What's step 2? Yeah, or as I always call it, find what you're looking for. So let's see, we have 0.628 grams of precipitate, and we need the molarity of lead-2 ion in the original solution. So we need to go from our precipitate to which compound? Why? Exactly, you need to look for the lead ion. So you're gonna go right here. All right, so let's do out the math. 0.628 grams of PbI2, because that's a precipitate. Our molar mass is a large 461 grams in 1 mole. And then we use our mole ratio here. What's our mole ratio? So on a test, well, you have to write it down. Exactly. Just skip it. If it's 1 to 1, then you know it's 1. So just, yeah. But I'm gonna write it for teaching purposes. For every 1 mole of lead-2 iodide. It's a terrible looking eye. For 1 mole of lead-2 iodide, there is 1 mole of lead-2 nitrate. Now, final piece de resistance. We're going to solve it out. We're going to get 1.362 times 10 to the negative 3 moles of lead-2 nitrate. We're done, right? Why not? But if you look here, how many lead ions are in lead-2 nitrate? So the molar, it follows the molarity of lead-2 nitrate is the molarity of the lead-2 ion.
But for explaining purposes, we can convert to the molarity, the moles of lead 2 ion.
For explaining purposes,
But you would just realize that it's a 1-to-1 ratio still, so you would end up with the same number.
so
That makes sense.
this is writing it out for continuity purposes. 1 mole of lead nitrate contains 1 mole of Pb2 plus ions.
So now our units match up to what we're looking for, right?
So now it's 1.362 times 10 to the minus 3 moles of Pb2 plus ion. All right. We have moles. We have volume. How do we get to molarity? Yeah, so our molarity, so step 3, find final thing. So molarity equals moles over liters. So 1.362 times 10 to the minus 3 divided by 38.5 equals
That's interesting.
yep.
2, 3, 5. Yeah, you can write that to the liters.
That is exactly what he purposely
Yeah,
did not write down.
yeah, I purposely did that. Oh, somebody was gonna catch me. 0.385.
Of course not. You caught it.
It's like a sigma in here. We're gonna have the Greek lithography class. All right, we solve this out. We'll get 0.0354 molar Pb2 plus ion.
Boom.
All right, questions about that?
What about people on Zoom? Any questions?
You understand this, my man in the rowdy brown shirt?
I mean, I'm not in this class, but.
I mean, yeah, I mean, if you can understand it, you're not even in the class, that's like a good indication, at least when.
Even if you slightly understand it, you know, that would be sweet. Interesting. Interesting. Can I get a thumbs up from the Zoomers? Yeah, 1 thumbs up. Thanks, Ewan. Wait, Ewan, a little birdie of mine told me you don't go by Ewan. Is that true? I mean, do you prefer? Okay. We'll go by Taylor from now on. Switch it up. And maybe later on we'll go by Ewan again. We'll switch it up. All right, Taylor. Awesome. Now we can go to number. Let's see. So number 16 is an interesting problem. I'll give you all 3 minutes to work on it, and y'all can go starting now. Start a timer for 3 minutes.
3 minutes.
What did you say?
How do you answer?
With the words?
Oh, okay. Well, I feel like, whatever. Oh, you don't know. Right.
Complicated.
Nothing.
All right, time is up. Does someone on Zoom want to explain their answer for A? And in case you didn't know, this was a word problem, so expected you would maybe like write a single sentence. Like that's like describe the effect of raising the temperature on the motion of CO2 gas molecules. How does increasing the temperature affect the molecules? Anyone on Zoom? Or my two Zoomers? Motion increases. Which motion? Like, it's vibrating faster. I mean, that would be true, but we're specifically talking about what when we talk about the motion? The collisions against the container wall, that's true. All right, so increased collisions against the container is a byproduct of, well, let's start with the most basic thing. So what is temperature the measure of, or yeah, what is temperature the measure of? Temperature. Temperature is proportional to something. Yeah. So temperature is proportional to the average kinetic energy. Okay, so that's what I was looking for. So average, and I'm going to abbreviate KE for kinetic energy. So if it's proportional, directly proportional, that means as we increase the temperature, so as we increase the temperature, the kinetic energy KE increases. If the kinetic energy of the molecules increase, what increases of these molecules? There begins with a V, and it's not volume, and not vibration. Let's say if you took physics at any point in your life, you know kinetic energy is equal to 1/2 mv squared, where v is velocity. Okay, so if you increase the kinetic energy, you increase the velocity. So this is the answer I was looking for, and you'd probably be looking for on the test. As you increase velocity, you obviously also increase other things. So like the what's it called? The amount of collisions on the container, and we'll learn how that affects another quantity. Okay, in part B. Calculate the pressure of the gas in the container at 425 Kelvin. All right, so we're only given what variables? This is, where's B? P and T. Oh, I reversed. T and P. T, and there we go. So we're given a before and after of temperature before the increase. We're given the pressure before the increase, and we're asked to find the new pressure after it increased to a different temperature that they give us. What equation should we use here? What?
Just the P1.
So it's P1 over T1 equals P2 over T2. Does anybody know what law this is that relates pressure to temperature? Yeah, it's actually Guy-Lussac's. But it is spelled that way, but it's Guy-Lussac's. Anyways, we're looking for P2, right? Because P2 is the pressure afterwards. So we solve for P2 by multiplying both sides by T2. So P1 T2 over T1. Plugging this into our equation, or everything into our equation, we get our pressure at the beginning was 0.7 atmospheres. Temperature at the end was 425 Kelvin. And our temperature at the beginning was 299 Kelvin. And putting this into your wonderful calculator, you should get an answer of 0.995 atmospheres. If you put that into your calculator. And what do we notice about as we increase temperature, what happened to the pressure? Did it increase or decrease? It increased from 0.7 to 0.995.
Whose law is that when the pressure increases?
We already went over that. We already went. Anyway, Rich. Anyways,
That's my favorite law, personally.
so it's important to realize that as we increase the kinetic energy, we're increasing the velocity of the molecules, which increases the number of collisions with the container, which is by definition will increase the pressure, because increased collisions with the container is going to increase your pressure, because that's how that works. All right. So I kind of just explained the C, but on the key I have at higher temperatures, the molecules move faster and will hit the sides of the container with a greater force, therefore increasing pressure. Okay. So that's the answer to C, if you're wondering. We're going to skip number 18 and we'll go straight to, no, we're going to skip 17 and go to 18. All right. I will let y'all work on this one. 3 minutes starting now.
3 minutes, counting down.
What? So in his PowerPoint, where the gas and all that. Does the K and the T matter?
K what?
So like it's like E equals KT. Does that matter?
Oh,
Does the K matter?
no.
Well, okay.
It's to tell, you remember those equations that were like, oh, the pressure is equal to the temperature times the constant.
Oh, yeah, the K.
And
The
you
K
never-
doesn't matter, yeah. No, the K is just like a regular.
Constant. Anyways, work on the problem.
Sorry.
Let's get our practice reps in. This is, we're like trying to be star athletes in general chemistry 1 by the end of the semester. The more practice you get, the better you're gonna be. At the end.
Oh.
We will give extra credit to the best person.
Extra credit?
Yeah,
Well,
possibly.
that's a tough one. Well, the best person will also probably end up getting the best scores. So I mean, naturally you'll do better than other people that don't.
Yeah, we'll talk to the Gen Chem 2 professors and give you an A+ in Gen Chem 2,
They can do?
for sure.
Can?
I mean, OChem's kind of pushing it. We'll see.
Yeah, it depends on how good you did in this class. Okay.
Now, if you can understand what's on that board right there, you pretty much know all of them.
Hey, Rich, does aniline prevent bromination when you have catalyst? Does it attack the catalyst? In other words,
Yeah. I know what you mean.
the,
Oh, no. Oh.
I mean, I don't think poly alkyl or bromination would take place.
so what would be the product?
Bromine, ortho, amino group.
Yeah, I think so too. Oh, man. The vibes last semester seemed different. All right, time is up.
All right, let's do this.
All right. Rich is gonna attempt to give it to you. All right,
Don't. Okay, suppose a student mixes 2.34 moles of zinc metal with excess HBr solution. Step 1, predict the products and write a balanced chemical equation of the reaction. What do you look at?
why?
Whole reaction? Y'all in the lab, Gen Chem 1 lab, have y'all done the, what equation, the zinc iodine experiment?
Yeah, that's tomorrow.
So you've done the lecture? Or no? You did the lab lecture last week for that lab.
Yeah.
So,
Done, right?
so then you should know how to do this.
Yeah. but
Silly.
I think it's-
So what's important to realize is what do we have here? We have a metal, right? And we also have an acid. What? Yes,
There we go.
there we go. She got her money now.
All right, so we got HBr plus zinc creates hydrogen gas and your salt, which in this case is NCnBr2.
Perfect. And you can assign, we know zinc bromide is going to be, is it soluble or
Why?
why? Okay, so zinc bromide is aqueous.
And then what about hydrogen? What's the state for that?
It
It
is
is
gas.
indeed a gas.
And what about zinc to begin with?
Yeah,
Just by itself.
well, it's
It's a
metal,
metal.
so it has to be this state, solid, yeah.
Yes, solid.
And what about HBr?
Yeah.
Yep. All right, so let's put this here. All right, and then is this equation balanced?
Yeah.
So what would you do to balance it? That's it.
That is it.
Relax, relax.
That's what she said.
You're my shirt.
Yeah. She's wearing it. That's what she said. Sure. So that's why I said it for people on Zoom. Okay.
Good show, by the way. Pretty good show.
If this,
The student collects the gas in a 4-liter container, 4 liters, measures the pressure to be 17 atmospheres, calculate the temperature of the gas. So what equation would we use?
what other equation, what other information were we given in the very beginning too? If it matters.
Yeah, you are given moles. You're given pressure, you're given volume, and you need to find temperature. So what equation would you use?
Perfect.
Indeed. PV equals nRT. So let's do the variable thing because people apparently like that. So we'll divide both sides by N and R to get T by itself. So these go away. So temperature equals pressure times volume over N times R. So solve that up. Pressure is going to be 17 atmospheres times the volume, which is 4 liters, over our moles. But wait, we have moles of zinc metal. So how do we get to moles of hydrogen gas? So what does that equal?
Oh, I don't.
Looking at the ratio here, what is the moles?
The B, the one.
Yeah. 1-to-1. So moles of zinc is the moles of zinc that we started with initially is equal to the moles of gas that is produced because it is 1-to-1.
So in that case, folding our arms, the moles will be 2.34. And then our R, what's the value for R?
R is a constant. So it's not out here.
Oh, you're saying
0 point close.
0.
0.821.
1. 821. Exactly. You said 8
So
2.
So R is always need that number.
R is always going to be that number until you get to Jankum 2. So for this class, R is 0.0821.
Yep. Now we'll solve that out. We'll get a temperature equal to 353.9 Kelvin.
Oh, Rich. This guy.
There we go. All right, any preguntas, as they say in Spanish?
No. You say this in Mexican.
It's not a random language.
Bruh. You know, Rich himself, he's actually like half Mexican. You know that, right?
Yeah.
Like 50, 60, whatever.
Yeah, exactly. I'm a racemic mixture of Mexican and Indian.
Exactly.
Interesting, I've never heard of that.
Wow.
Well,
Well, I've
they're-
never met anyone.
All righty.
they're more of a-
Number 19. Question 19.
All right, calculate the density of oxygen gas at 453 Kelvin and 0.75 atmosphere. That's all the information you need.
Calculate the density of O2 gas at 453 Kelvin and 0.75 atmospheres. Density. Start with the most basic equations that you know. And try to manipulate them in a way to solve this problem. This would be a challenge for anyone, maybe. I can do this one.
All right. Make sure to derive the equation.
Oh, of course. That's my expertise right there. I know that equation by heart.
Yeah, that equation, you gotta show how to get to that equation.
Oh, we know. What is the equation for density?
Now,
Perfect.
volume.
Interesting. Density equals mass over volume. I'll help you all with that.
Volume.
Think outside the box, silly.
So you're looking for density and now you're looking for volume.
Exactly.
But you only have one variable. You don't have volume.
Think outside.
Oh, wait.
This is good. Let's go with CLT. though.
Yeah, let's get those think pair share going on. All right, well, we're gonna give you less time on this because I see a lot of. What about people on Zoom? How y'all finding it? How y'all coming along? Throw it in the chat. Hey, y'all should tell all y'all's friends to start pulling up to these sessions. Let's get it like,
I don't talk to anyone in my class.
then,
Yeah.
then talk to people,
Yeah.
then talk to others.
So you talk to her, she talks to the class. That's just how it goes.
perfect. Then say, hey guys, look, there's great people.
Wait, no one's responding online. We give them the option of being online.
That's okay, they want to be online.
No,
Some people,
they
some people don't have class today
can get around.
and they live 40 minutes away.
I live 30 minutes away.
That's
But you
great.
have class, so
Yeah,
you were already on campus.
like 2 hours.
No, no, crap.
Okay. Okay, all right, time is up. So, we're given what variables to solve for density? Temperature and pressure. If you're given these variables, and you're like, well, density equals mass divided by volume. Temperature and pressure aren't any of those variables, right? So think of another equation that we know that has temperature and pressure.
Well, we're all in right now, this screen.
Well, I'll give you the equation that we should be thinking. PV equals nRT. Okay. What do we also know about one of these other variables in this in the second equation? So R is a constant. That's not really going to give us too much info, but good guess. We also know that the moles, which is abbreviated N, is equal to the mass divided by the molar mass of a compound. Okay. Okay. What?
The mass, the molar mass. The mass of those two is the molar mass.
Really?
Where's the mass from?
So watch this. So we're gonna incorporate if n is equal to m over molar mass, we're gonna substitute this n into there. So PV equals the mass times RT over the molar mass. We also know that density is equal to mass divided by volume. We have mass and we have volume. Watch this. Keep your eyes on the screen. If we solve this equation algebraically to get mass over volume, you would multiply times molar mass and divided by RT on both sides, and you'll get, and we'll divide by V on this side. So you'll get M over V is equal to pressure times the molar mass over R times the temperature. Look at this. M over V is density. So this is equal to density because that is true. D equals M over V, which is equal to P times the molar mass over RT. Guess what that gives us?
So
We know-
can you use the pressure times molar mass, or whatever equation to solve for the density of, say, a solid? I'm asking you that question. Well, not you, like anybody.
Think. Can you take a wild guess?
Yes.
Does a solid have pressure? Solid has no pressure. Or technically, we're not going to go into any physical chemistry, okay? But for this class, a solid has absolutely no pressure because it's just stationary, it doesn't move, it doesn't take the shape of its container. Okay. So no is the answer to Rich. Anyways. Plugging in all of our variables, we have a pressure of 0.75 atmospheres. The molar mass of O2, the molar mass of oxygen is 16 grams per mole. So O2 would be 16 times 2, which is 32 grams per mole. R, what is R?
0.0821.
0.0821. I don't care about writing all the units. It's liters, atmospheres over mole Kelvin. Okay. I'm not going to write it. Temperature is 453 Kelvin. Plugging this in, you should get that oxygen has a density of 0.6 19.64 grams per liter at that temperature. Okay, and that pressure specifically. So look at that. You have to use things outside the box, and you're probably going to get a question like this on your test, because I know I did. So instead of deriving this equation, it's also pretty nice just to memorize this. M over V is equal to P times the molar mass over RT. And you don't have to just apply this to problems that are asking for the density. Anytime you're given, let's say, an equation or a problem where it gives you the mass of a gas in grams, normally you would have to go from grams and convert it to moles, but you can just plug all that in here and find your variable that you're looking for, because you already have the n in here. It's just plugging in things, and I can show you what I mean by that in a separate question. I guess I can show you that now. So what a question would look like that I'm talking about. So let me make a question. Let's say, give me a gas, a different gas that has a way larger molar mass. Let's do chlorine. So a sample of Cl2 gas has a mass of, let's say, 120 grams at a temperature of 400 Kelvin in a 7-liter container. Okay, sorry. What is the pressure? So P, question mark. Answer this question right here. Not the number 20, this one here. So the way I would have done it is, it gives us mass, and normally what people will think they have to do is 120 grams of Cl2. Molar mass of Cl2 is 35 times 2, which is 70, plus 0.9, so 70.9, I think, 35.45. Yeah. So 70.9 grams per 1 mole equals some number, blah, 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 blah. And they'll plug that number into their next equation, PV equals nRT. What I would have done on the test is you straight up when M over V is equal to P times the molar mass over RT. We're looking for pressure, so we solve for P, so P is equal to M times RT over the volume times molar mass. We plug everything we have in here, so the mass was 120 grams, R is 0.0821, T is 400 Kelvin, volume was 7 liters, and then molar mass is 70.9 G per mole. Plug that into your calculator and you'll get the same answer as if you had done the stoichiometry first and then plugged in PV equals nRT. So this is a way to quickly solve problems that are like this, instead of, I guess, a faster method. So that's how I would have done it personally. You can choose whatever works for y'all. With that being said, that is the last thing we will do. And our session, I'm just talking to y'all at this point. And whoever else, this amazing person that stayed in next, oh, Taylor, look at her. Look at All-Star Taylor. No wonder Taylor rhymes with All-Star. It does not. Anyways, yeah, so we have another session tomorrow at 2:30. Please, you should tell all your friends, Taylor, everyone in the room, even if you're not in this class, you should tell them, hey, go to their sessions. I promise you, it'll only help you. And tell them that if they're pre-med and they want to do well in this class, that they ought to really be going to our sessions if they want to have the best grade possible for themselves. Anyways, that's it. Rich, you have anything to say? Thanks, Taylor.
Yeah, tell everybody to come to the sessions, make people pull up. Get the Greek letter guy to show up, actually. I need him to do his push-ups.
No, you don't.
It's crazy.
All right, well, yeah,
How many people do show up to this class?
he said 60 came today out of 90. Anyways, yeah, y'all have a good one. Again, please tell all your friends, and maybe someone could take a stand and say, guys, please go to these